Swayam Prabha. Digital India. Educated India.
So, I have already finished two modules. The first module I have discussed about the causes of earthquake. As we have already mentioned that this is due to the movement of tectonic plates and rupture of rocks along a fault. So, I have discussed the causes of earthquake, then the what are the different types of seismic waves, that the body waves and then the surface waves. Body wave, it is two types, one is primary or compressional wave or P wave, another is secondary or shear wave or S wave, and then the surface wave, two types, lava wave and the Rayleigh wave. And then I have already discussed that the locating the source of earthquake. So, two ways you can locate that I have discussed, that if your velocity of the wave that is known, then we can use this expression and then we can determine the d, the distance between the focus of earthquake and the site of interest. And then generally we can take a velocity of shear wave 3 km per second, range is 2 km per second to 5 km per second, and the P wave velocity is 6 km per second, range is 3 km per second to 8 km per second. So, that means if it is shallow earthquake, then this d we can treat as the distance between the epicenter to the site of interest. But remember that is applicable if it is a very shallow earthquake, and that means the distance between the epicenter and the focus is very less, and the wave is traveling through the crust only. So, that is why if it is crust, then we can consider the velocity of P wave as 6 km per second or the velocity of S wave as 3 km per second. So, and next, that if we don't know the velocity of the P wave or the S wave, then we can use this distance versus travel time graph, from where we can also determine the distance from the site of interest to the epicenter. But in all the cases, we will get, if we take the one seismograph data or seismograph data, then we will get the only the distance between the epicenter to the location, but we will not get the direction. So, to get the direction, we need at least 3 seismograph data to get the location of epicenter, and that I have already discussed. But remember that these are the preliminary determination of epicenter. So, more refined estimation of epicenter or hypocentral distance or the location is done by multiple seismograph data. Then we have to use more seismograph data and 3D seismic velocity model of the earth and numerical optimization technique. So, these will give us the preliminary idea about the location of the epicenter, but if we accurately want to locate the epicenter, then we have to use more seismograph data, then 3D seismic velocity model of the earth and numerical optimization technique. Then we have discussed about the size of earthquake, then earthquake intensity, what is earthquake intensity and earthquake intensity based scale, then earthquake magnitude and the earthquake magnitude based scales and their relationship also I have discussed. Then in the next module, that is our strong ground motion, module 2, where we discuss that how to measure the ground motion. Okay, there I have already discussed, and the three significant ground motion parameters. These are significant parameters. In addition to that, there are few other parameters also those I have already discussed, but three significant parameters are amplitude, frequency content and duration of the earthquake. In the amplitude parameters are acceleration, velocity and displacement. These are the major amplitude parameters, acceleration, velocity and the displacement. And so that means in the measurement we can measure the acceleration and time history, or we can measure the displacement and time history. But if we measure the acceleration, then we can get the velocity and the displacement by integrating that, and if we measure the displacement, then we can also get the velocity and the acceleration by differentiating that. So, we will get these parameters. Then the frequency content parameters. Sometimes these frequency content parameters are also important, and those are Fourier spectra, power spectra and the response spectra, and these are I have already discussed. And this is the Fourier spectra, that means your plot between the Fourier amplitude and the time period of frequency is called the Fourier spectra, and I have already discussed that how we will get the Fourier series by using one example problem also, and then from there how you will get the Fourier amplitude, and finally you will get the Fourier spectra. So that I have already discussed, that means this is plot between Fourier amplitude versus the frequency or the time period. So, that means here first we have to express it in the Fourier series, then from the Fourier series we will get the Fourier amplitude, and I have already discussed how we will get that. Then we have power spectra, and then we have a response spectra. So, response spectra also I have discussed that this is basically the earthquake resistance design structure. In structure, entire time history may not be required. So, we need the maximum value or the absolute value of the response of the structure to a particular base motion. Okay, so I have already discussed about the different response under different loading conditions. Okay, harmonic loading, then the periodic loading. In periodic loading, we have to convert this load to a series of number of harmonic loading. So, that means that we will convert it to Fourier series, and then we will get the response, and then we will get back to the response of that your input motion. So, now that means there may be the acceleration response spectra, velocity response spectra and displacement response spectra. So, I have already, as I mentioned, I have already discussed the displacement, how to get the response of different kind of loading condition or different type of condition, different type of loading I have discussed, harmonic loading, periodic loading, step loading, pulse loading, and then from there I will get the response that I have also discussed. I have discussed few example problems also where we will get the response of that single degree of freedom system. Now, from the response spectra, as I mentioned, that here you will get the your that response spectra. That means here I have already discussed that from here that we will get the response of different loading conditions, and I have solved by simple example. Now, for any earthquake loading also you will get the say response of a particular structure, and for different time period if you get the maximum displacement say of that structure, maximum displacement, you will apply the same motion, base motion in that structure, and then you will know the time period or the natural frequency or the time period of the structure, and we will get the response of that structure or the displacement of that structure, and from there we will get the maximum displacement, and that we will get for that corresponding time period. natural time period or the frequency. Then for next another time period or natural frequency for we will get the another maximum displacement, and so on. You will get the maximum displacement with different time period, and that if we plot, then I will get the displacement response spectra. So that I have discussed by example problem also. So we will get the, but I have discussed with the simple problem, but here you can use the any your base motion, and then in that case the maximum value of acceleration, velocity and displacement depend only the natural frequency and the damping ratio, that I have discussed, and the maximum value of acceleration, velocity, displacement are referred as spectral acceleration, spectral velocity and spectral displacement. And so I have discussed that how I will get the displacement response spectra by using the maximum displacement with different time period or natural frequency or time period. So, but if you have the expression for the acceleration and the velocity, from there also you will get the maximum acceleration and the maximum velocity with respect to different natural frequency of the structure or the time period, and then if you plot that maximum acceleration and the time period or the maximum velocity and the time period, then you will get that acceleration response spectra and the velocity response spectra. Clear? So, I have discussed this displacement response spectra. Then if you get the expression for the acceleration and the velocity, then here the expression of acceleration, velocity, time histories, then that can be obtained by using Duhamel integral. So, Duhamel integral can be used to get the response of under any arbitrary loading. So, if you get for any base motion, if you get the expression by using the Duhamel integral for the acceleration, velocity and the displacement, then if you get the maximum value of this acceleration, velocity and displacement, and if you plot them, then you will get the acceleration response spectra, velocity response spectra and displacement response. The spectral acceleration and spectral velocity is sometimes or often approximated by using pseudo your spectral acceleration and pseudo spectral velocity. Okay. So, and that I have already discussed that how we use the pseudo spectral acceleration and pseudo spectral velocity by using that omega 0 natural frequency. For the velocity, if we multiply the factor omega with the maximum displacement, then you will get the pseudo spectral velocity, and if you multiply with the omega 0 square, then you will get the pseudo spectral acceleration. So, now remember that these are not the true acceleration or the velocity, but often but they are very close to the true value, but often this spectral acceleration is represented by pseudo spectral acceleration and spectral velocity is represented by pseudo spectral velocity. So, now the next part I will start the or in the next part I discuss about the estimation of ground motion parameters, and I have discussed about different attenuation relationship for the estimation of ground motion parameters, and then I discuss two example problems that how we use those attenuation relationship for one deterministic seismic hazard analysis and one is for probabilistic seismic hazard analysis. Though I have not discussed in detail about this seismic hazard analysis part, as that was not the part of this course, but I have just discussed that how to use those attenuation relationships. Now, this today's class I will discuss about I start about my third module, that is the measurement of dynamic soil properties. Now, this class I will first discuss about the field test. Okay, then I will discuss about the lab test and the model test. Now, field test, before we go to the field test part, then there are different types of tests. So, few are categorized as the low strain test and few are categorized as the high strain test. Now, what is low strain test? Low strain tests generally operate at strain level that are not large enough to induce significant nonlinear stress strain behavior in the soil. The typical shear strain range below which it is called a low strain condition, that is 0.001%. So, now if our test where we will get the strain level below 0.001%, then those tests are called low strain test, and if it is more than 0.001%, then it is called the high strain test. This is a normal guideline. So, now in the field we can perform different low strain test and different high strain test also. So, low strain tests are, that is seismic reflection test, seismic refraction test, seismic crosshole test, seismic downhole test, all spectral analysis of surface wave test. So, these 5 tests I will discuss, and these tests where your shear strain range is less than 0.0003%. and low strain is 0.001%. So, it is 0.0003%, that means it is in the low strain range. And what is high strain tests are? These are SPT, standard penetration test, CPT, cone penetration test, dilatometer test, pressure meter test. So, these tests, all these tests I will discuss one by one. So, first I will start about the seismic reflection test. Okay. So, here seismic reflection test, you can see these are all the geophones or the receivers. Those are placed with some distance, and this is the source where we will generate the wave, and these waves will be received by the receiver. Now the one option, this wave, when we generate the wave will travel in infinite direction. So, the possibility is that the wave will reach directly to the receiver and wave will reach by reflection if we have 2 different layers. So, that means here it will reflect. Right now, we are only concentrating on the reflection. Later on, we will discuss about the refraction also, but right now we are only concentrating on the reflection. So, that means here that wave will reach directly to the receiver or by reflection. Now, based on that, we can determine what would be the velocity of the wave and what would be the thickness of the layer. Okay. Now, let us discuss about that how we can generate this wave. And now, if we generate the wave, you can see that if we generate the wave in different form. So, first one, say this is my ground surface and we will do a small explosion. Okay. So, that means we will do shallow explosion. We can do shallow explosion and from there the wave will generate. Okay. Now, this type of generation, this is my ground surface and just we will do a very shallow explosion. So, this is shallow explosives. So, this is rich in P wave content. So, that means if I generate the wave in this form by conducting a shallow explosion, or here it is shallow explosives. So, then the wave that will be generated will be rich in P wave content. Okay. And now, if another way we can do that, suppose this is my ground surface and if I do a vertical impact by hammer blow. So, we will get a vertical impact on the ground surface and then also it will generate wave in different direction. So, this will, that is my vertical impact. Okay. So, this will be also reach in P wave content. Okay. So, if I make a vertical impact on the ground surface, then the wave that will generate, that will be also reach in P wave content. But if I make this type of horizontal impact, suppose we have a metal rod or block, okay, and that is on the keeping on the ground surface, and then I will make this type of horizontal impact on that side of the block. I will make an impact on the side of the block, and that means this will be the impact, and then the wave will generate. Okay. Now, this is this type of horizontal impact. Now, that will be reaching SH, that means shear wave horizontal component, SH content. So, that will be, these are the different way we can generate the wave, but depending upon how you are generating the wave may be reaching P wave content or may be reaching SH content. Okay. So, this way I can get the velocity of the P wave or the S wave, and now if I get the velocity of the P wave and S wave, then based on the correlation we will get the shear wave or the other properties of the layer. Now, first if I discuss about our first type of that is seismic refraction test. Now, first we will discuss that. So, suppose this is the first one is the seismic refraction test, the first one I will discuss. Okay. So, first is the seismic reflection test, and that is for horizontal layering. That means if the layer is horizontal. So, suppose this is the ground surface and this is the horizontal layer, this is the layer. So, this is my layer 1 and this is layer 2. Okay. So, this is the source. Say A is the source where I have generated the wave, and I have discussed how to generate the different types of wave. And then this is the position of my geophone or receiver. Okay. So, then there will be the wave will travel in the n number of direction. So, from this n number of direction, one wave that will reflect and that will reach to the receiver. Now, which wave? Depending upon where you have placed your receiver. So, if you placed your receiver in left or right, then another different wave will go to the receiver, because okay. So, that means if you place it here, then another different wave will reflect between the two interface or the boundary between two layers, and then you will reach. So, I have considered these wave because it is received by the receiver and because it is placed here. So, where is the distance? The distance is the x, is the distance of that receiver from the source. So, A is the source, C is the receiver or geophone, and this is point B. So, I can write that the travel time for the refracted ray, or here say it can be P wave, it can be S wave, depending upon how you are generating that. Right now in the all my derivation I am writing it is P wave, but depending upon how you are generating it can be SH wave also. So, I am writing it is P wave say. So, what will be the reflected wave? So, this is my reflected wave. So, the travel time will be T AB plus BC root over VP1. So, VP1 is the P wave velocity of layer 1. Okay, so VP1 is the P wave velocity of the layer 1. So, that will be the travel time of the P wave. Now, as I mentioned, there will be another wave that will reach directly from A to C, because waves are traveling in number of direction, isn't it? Okay. So, there will be two waves, one will be direct wave, another will be reflected wave. So, travel time for the direct wave that if I say TD, that will be x by Vp1, because this is x, Vp1 is the velocity, I will get the travel time. So, now if I draw, this is alpha say, and this will also be alpha. So, what will be tan alpha? Tan alpha will be, this is Z say, or you can say this is H1, thickness of the layer 1. H1 is the thickness of the layer 1. So, alpha will be x by 2 into H1. Okay, tan alpha will be x by 2 H1. So, now I can write that my AB, that will be equal to BC, that will be equal to root over, this is H1 square plus x by 2 whole square, this is x by 2, this is H1, so this value is root over H1 square plus x by 2 whole square. So, now if I put this value here, then T will be, this is BC, AB is equal to BC, so this will be 2 BP1, then root over H1 square plus 2, plus x by 2 whole square, plus x by 2 whole square. So, if I get this value, and then if I simplify it, then or I can write it is in different form, that is equal to H1, that will be equal to H1, that I can write half root over Vp1 t square minus x square. So this so that means x is known to me, because x is known to, why x is known to me? Because x is the distance from the source to the receiver, that is known. So x is known, but h1 is unknown and Vp1 is also unknown. So now we have two equations and two unknowns. So from here this I will get the Vp1, because I can get the travel time of the direct wave. How I will get? But I know at what time I have generated the wave from the source, and at what time it is reached by the or received by the receiver, then that two times I can know. So this difference will give me the travel time of the direct wave from the source to the receiver. And it is obvious from this diagram also you can understand that the direct wave will reach before the reflected wave. That is confirmed. So first wave that will be reached will be the direct wave, then the reflected wave will come into the receiver. So that way I will get the direct wave travel time also, I will get the reflected wave travel time also. So both T and TD are known. Okay, both. So from here I will get from this expression I will get the Vp1, and now if I put this Vp1 here, because T is also known, Vp1 is also known, X is also known, I will get the H1. That is simple. But the problem is that here we are using only one receiver data, and there is a possibility of error. Now to reduce that error, we can take the multiple receiver data. Now if we put another receiver here, so if I put n number of receiver, then I will get the multiple receiver data, and but the expressions are same, whether it is a single receiver or multiple receiver. Now if I get the multiple receiver data and if I plot them, so suppose this is my distance x, this is x, and this is the travel time t. Okay. So now I have two equations. So one will be equation number 1, another will be equation number 2. Now equation 1, that will give me the direct wave equation. So that will be a straight line. That will be a simple straight line. So and the slope of this line will give me 1 by Vp1. The slope of this straight line will give me 1 by Vp1. Remember that here I am using multiple data, because I know the travel time of the direct wave for first receiver, second receiver, third receiver. So if you know the distance of first receiver, you know the travel time, you will get this point. For the second receiver, if you know the distance and we know the travel time of the direct wave, I will get the second point, third point. This way I will get these points. Okay, and if I join those points, I will definitely get a straight line. So basically I will get those points, then I will join and I will get a straight line. It is not that first I will get the straight line, then I will plot the points. No. First I will get the points, then I will join them, I will get the straight line, and the slope of the straight line will give me 1 by Vp1. That is equation number, this is equation number 1. This line is following the equation number 1. Now you go to the second equation, that will give me a equation of an high parabola. Okay, in the second one, this is my equation number 2. Okay. So, here there may be a possibility that suppose I will get, there is a possibility that I will get, so suppose this is my geophone number 1, so I will get a data up to here. So, I will get a data up to here. Okay, and next then I can extend it and up to the y axis, and that line will give me say T0, say T0. So, I will extend it, I will get the T0. This is my real data, then you will extend it. So, this is will give me the high parabola expression. This is a high parabola. Okay. So, now from here what I will get? I will get VP1, and that will give me the average value of VP1, not a single geophone. I will get the VP1. Now, if I extend this equation to this plot, this hyperbola plot, extend it, then I will get T0. What is T0? The T0 is the T is equal to T0 when x is equal to 0. Now, if I put this value in equation 2, then I will get from the equation 2 that T0 will be equal to 2 by Vp1 into H1, because x is 0. So, from here I will also get that H1 will be equal to T0 by 2 into Vp1. T0 by 2 into Vp1. So, from here I will get T0 from where? T0 from the plot, and then Vp1 I will get also from the slope of the equation 1, and then I will get the H1. It is simple. But the one issue is here, that here the first equation, drawing the first line is not a problem, because I know that will be a straight line. The point that I will join, I will get a straight line, that I know. But the second one, drawing a hyperbola with different points will be difficult. Okay. So, to avoid that, what we are doing, that we are basically squaring the equation number 2. So, if I square the equation number 2, that will be T square, then 4 Vp1 square, then H1 square plus half x whole square. Okay. And then if I further simplify it, I will get that 1 by Vp1 square, that will be your x square plus 4 H1 square, and T square will be x square by Vp1 square plus 4 by Vp1 square into H1 square. Now, if I plot another graph by using this equation number 3, the similar plot, if I plot by using equation number 3, this is also distance and this is the time, but here it is time square, and this is also distance square or x square. This is t square. So, that means this is t square versus x square, and the x axis is x square and y axis is t square, and this equation also t square. Then now this equation will be a straight line. a simple straight line. So I can join by a straight line, simple straight line. Similarly, again this will be our first point. Here also first point, second point, third point, fourth, fifth, and like this. I will get the n number of points, and then I will, now I know this is a straight line, so I will join them, I will get a straight line. And now if I extend this straight line, I will get T0 square. Now by using single plot, the slope will give me what? Slope will give me 1 by Vp1 square. And now if I extend this, so T square will be equal to T0 square when x square will be equal to 0. Now you put that, here it will be T0 square equal to 4 Vp1 square and h1 h square, or I will get here simply h1 will be equal to half T0 Vp1, the same. So by using the same single plot, now I will get the Vp1 as well as the h1. But the advantage of the third equation here I will get the straight line. So again drawing the straight line is very easy. So by now I will get the n number of geophone data. I will get plot them in x square versus t square. I will get by one single straight line, I will get the Vp1 as well as the thickness of the layer. So this is the case if it is a horizontal layer. Now if the layer is inclined, what will happen? So that I will discuss in the next class. So next class I will first discuss for the seismic reflection test for inclined layering. Then if possible I will discuss the seismic refraction test also. Thank you.